Okay, it's 11. How are y'all doing? Good. Okay, we have a test on Wednesday. I sent a review out for that, a topic list on Friday or something like that. Everyone got that through your email? The test will stop at Harmonic Series, which we will cover today, but we're also going to continue to move along, okay? But the test will actually stop at Harmonic.
So yes or no on that?
Pardon?
Yes or no on Harmonic?
Harmonic, yes. Okay. So just a quick recap of what we talked about last time is that, and this I'm going to need this today, is that if we have an infinite series, right, that sum may or may not converge. And that's kind of like the whole idea right now is to figure out when a series converges or diverges. So if it converges, then we're going to call that sum capital S, right? So the sum of this is capital S. If we were to then look at this sum, what is this? This is not the infinite sum. This is the finite sum. In this case, we would call this the nth partial sum. We defined this earlier. I called it the kth partial sum, but it's summing all the terms of this sequence out and stopping at a certain place. In this case, I'd stop at n, right? So I'd do a sub 1 plus a sub 2 all the way to a sub n. So this is the nth partial sum. Capital S, which is the sum of the infinite series, is equal to the limit as n goes to infinity of the partial sums. So this is where I was saying that when you take a sequence and start adding up the terms, you create a new sequence. And the limit of that sequence is the sum of the infinite series. So this is from last class. I just want to make sure I have it like formally on the board. You're going to see me use this today, all right? I'm going to figure out what the formula is for the nth partial sum, and then I'm going to take the limit as n goes to infinity, and when we get that answer, I'm going to say that's the answer, and this is what I'm using, all right? Okay, now we finished up with geometric series. I should say we are not done with them, but we talked about geometric series, and we have basically one major result, right? The major result is this. When we have a geometric series, which was one of the common series, we would say we'd be looking at a series that looks like this. And that series will converge sometimes and diverge sometimes, and it all depends on what. What is the one thing that's going to determine the convergence or divergence of a geometric series? R, okay? R is what determines it. So this will converges if what? Absolute value of R less than 1, and diverges otherwise, right? So on your homework, those first few problems I asked you to look at should have addressed some of this. Now, any questions on those first few problems? No? I know I had some questions like right after class last time, but all that squared away? Okay, so let's at least get started today. I'm going to give us a geometric series, all right? But for this one, I think I'm going to make it alternate. Okay, so as an example, let's take this one. I want us to find the sum of, let's go with 3/4 minus 3/16 plus 3, trying to think of what I want to do here. 64. Let's see if we can pick up the pattern off of just that.
4 to the n plus 2 in the denominator.
So you're seeing that the denominator is powers of 4?
Yeah.
Everyone see that?
4 to the n plus 2, I think.
Yeah. So the whole goal, if I say find the sum, I told you this last class, if you see find the sum or find sum, what does that tell you right off the bat? It's either geometric or one of the ones we haven't talked about yet. Collapsing, okay? That's how you'll know. So right now, if I say find this sum, it's geometric, all right? Or telescopic. But so for this, we have to somehow turn it into this and then determine what R is. Oh yeah, by the way, we didn't put it up here, but when it converges, what does it converge to?
1 or 0.
A over 1 minus R. Right? That was this sum actually becomes A over 1 minus R. In the event that the absolute value of R is less than 1, then this sum will converge to that number. Okay, so here we need to see if we can't figure out how to write this in a condensed infinite series form. So we notice that the numerator is always 3, right? Also, it's alternating. How do we take care of the alternating part? Negative 1 to the what power here? We can do n minus 1 or n plus 1. Either one. I heard n minus 1 first. Will that work? That should work. If we plug in 1, we get 0. Negative 1 to the 0 is 1. So that would give us a positive number. And then if we plug in 2, we get 2 minus 1, so that's 1. So we'll get negative 1. So that should get us our alternating. We also know that the numerator is always 3, right? So I'm going to put 3 on top times 3. And then the bottom appears to be 4 to the n, right? Because that's 4 to the first power, 4 squared, 4 cubed. Okay, so there. We have a formula that represents that series. Now we need to make it look like this, right? We need to make it look like this. So how about that 3? That 3 is always just 3, right? I mean, it's not controlled by n at all. So I could actually pull that out of the series completely. I could rewrite this as 3 sum n equals 1 to infinity of negative 1 to the n minus 1 over 4 to the n. Yes?
Could you use that as A? Or?
You could use it as A. Yep. It could be part of it. Or you could just save it at the end, multiply your answer times 3. It's really up to you. If you want to have that 3 in there, go ahead and leave it. I'm just going to pull it out. Yes?
Say it's more work to leave it in there.
More work? Maybe. Yeah. It's just a factor. It's just a number, right? That's going to multiply through. So I don't think it's trouble either way to leave it or take it out. Okay, so what can I do here? What am I trying to get to?
You just take the limit of this one.
Yeah, this one's already to the n minus 1, right? Which my formula has n minus 1. So it would be nice if this was also n minus 1. So this is where I make it n minus 1, right? I go negative 1 plus 1 there, right? And so now this becomes 3 sum n equals 1 to infinity, negative 1 to the n minus 1 over what? 4 to the n minus 1 times 4, like that. 4 to the 1 if you want. Yep, I can do it that way. All right. So that 4 is on the bottom, right? And I could actually take that 4 all the way out and have it join the 3/4, or join the 3 and become a 3/4. Or you could leave it in and let that be your A. It's totally up to you. You're going to wind up multiplying a number through at the end. So you have some control of this, all right? So let me go to my next line here. So I've got, do you want me to pull the 4 out? I mean, I pulled the 3 out.
Yeah.
Okay, I'll pull the 4 out. It's going to come out on the bottom, though. 3/4 sum n equals 1 to infinity. Okay, so now we have negative 1 to the n minus 1 over 4 to the n minus 1. Since those are both to the same power, I can rewrite it like this. Right? That's the same thing. I have to put them together because the formula, right, has just some number r to the n minus 1. So I tried to make it look like that. There's a number r to the n minus 1. And what's a for us? If we're ignoring this, the a in here is a 1, right? Or if you want to move it back in, your a is a 3/4. It's your call there. Okay, so we are geometric now? Yes? We're geometric with a being 1 and r being negative 1/4, right? Negative 1/4. So we are going to check to see if this converges. So we take the absolute value of negative 1/4, and that is definitely less than 1. Check, it converges. Now, what does it converge to?
A over 1?
A over 1 minus r, right? So that means that this sum is going to become 3/4 times a, which is 1, over 1 minus what? Negative 1/4. So be real careful with that because it's 1 minus r. And if r is negative, then it's going to become plus after you subtract, right? We're almost there. Okay, so now this becomes 3/4 times 1 over, what is that bottom? 5/4. So I think at the end of this, did we just get 3/5? 3/5 at the very end? You get 3/5.
This represents the number it converges at, right?
That's right. So if you were to get on your calculator and do 3/4 minus 3/16 plus 3/64 minus, and keep doing that, right? The further and further you go, 3/5 is really what? 0.6? 0, 0, 0? That's what that is? So if you were to do this, you would get closer and closer and closer to 0.6. You would never actually be there, but you would get closer. Like, look, right there, if we just do the first term, where are we? 0.75, right? 3/4? 0.75. So then you subtract something from it. And then you add a little something and subtract. So what happens is you get closer and closer to 0.6. If you could do it forever, that is 0.6.
So we can use A like 3/4, right?
Mm-hmm. Yeah, if you wanted to use 3/4 here for A, then the only thing that would change here is that would have been a 3/4. But you get the same answer. Okay, good? That's an alternating example. So there's kind of a couple of layers to this. You know, you have to create the formula, right? So you're given a series, you have to turn that thing, find the formula for it, and then make that formula look geometric, and then from there identify your R. Okay. You're ready for harmonic? Yeah, let's go with harmonic now. Right. So a geometric series, as we've seen, has to look a certain way, right? A times r to the n. And anytime we see that, we're going to check the r to see if it converges or diverges. Harmonic series all have a certain look to them also, right? This is what they look like. Sum n equals 1 to infinity of c over n, where c is a real number. So c is a real number, but non-zero, okay? Obviously, if c was 0, this would just be 0 plus 0 plus 0 plus 0. But as long as c is not 0, then this is a harmonic. So let me give you an example of a harmonic. Sum n equals 1 to infinity of 1 over n, which would be 1 plus a half plus a third plus a fourth plus dot, dot, dot. Do y'all agree that that's harmonic? What's C? 1, okay. And notice that the denominators, they just keep growing, right? They just keep growing by 1. Here's another example of a harmonic. Is that harmonic? What's C then?
1.
1/3. See, where did, if I replace that number with 1/3, it's really like putting a 3 down here, isn't it? Right? So this is actually a harmonic with C being 3. I mean, sorry, 1/3, which creates this, right? But the important thing is the denominator, right? Look at this denominator, n, it's linear, right? N to the first power. 3n is linear, isn't it? And so what happens is these denominators keep growing, but they grow by the same amount each time, right? Jumps by 3, jumps by 3, jumps by 3, jumps by 3. Here, jumps by 1, jumps by 1, jumps by... We look at geometric, that's not what was happening, right? Like in the previous example, we had 3/4. The next one was 3/16. The next one was 3/64. So those denominators were going up exponentially. These are going up linearly. Agreed? Anytime you have a harmonic series, right, we want to check to see if it converges or diverges. And I've got great news for you. Great news. They always diverge, no matter what. Always diverge. It is not possible to have a convergent harmonic series. It is not possible. All right? Now, I'm going to try and convince you that that's true. All right? I'm going to try and convince you that a harmonic series diverges. And the way I'm going to do it is I'm going to try and convince you, well, I don't know. I've never done it off the general one. Should we try it off the general one? Yeah, let's try it off the general one. Try and convince you that this right here, I'm trying to convince you that that diverges, all right? So here we go. This right here is equal to C plus C over 2 plus C over 3 plus C over 4 plus C over 5 plus, this is going to be hard to do, plus C over 7 plus dot, dot, dot. Yeah? This is going to be hard. Can we do it with 1 first and then we come back to this? Because if we do it with 1 first, I think you'll see what we need to do. If I do it right here, I don't think you might have trouble seeing it. Let's just change the C to 1 for now. All right? 1, 1, 1, 1, 1, 1, 1, 1. And I'm going to go out a little further. There we go, plus dot, 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 right? Okay, so what we're going to try and show here is that this thing blows up, right? Becomes infinite. So we have first the number 1, right? Okay, we have the number 1. Now, the next number we have is a half. Plus, now what I'd like for us to do is take a look at those two numbers right there. Get a common denominator between those and put them together. So what do we get if we put those together? 7 over 12. Right? 7 over 12. Now, when we put these two together, 7 over 12, do you all agree that's bigger than a half? Because 6 over 12 is a half, right? This is 7 over 12, so this is bigger than a half. Okay. Now what I'm going to do is take a look at the next, not 2 terms, but the next 4 terms. Okay? Now, if we put those together, how big is that? So I don't want to get a common denominator here. That's going to take too long, right? But would you agree with this? This number is bigger than an eighth. Is that bigger than 1/8? Bigger than an eighth? Bigger than an eighth? 1/8, right? So would you agree that this right here is bigger than 4 1/8ths together? Right? So I'm going to change this. If this right here, right, this sum is actually bigger than the sum I'm showing you. It's 1 plus a half plus 7/12 here, but this one was too hard for me to deal with. But we said that this right here was the same as 1/8 plus 1/8 plus 1/8 plus 1/8 Those four together, but that's what? That's a half, right? So recap. Those four together are bigger than a half, right? Those two together are bigger than a half, but I just left it as 7/12. So this sum right here is smaller than that sum so far. Okay, now what? Plus, how far out should I go?
6?
8.
All the way out to this. Okay, go 8 terms. Now, let's see why. Why did I have to go 8 terms here? Because the last one is 1/16, right? I need each of those to be bigger than 1/16. Put them together to get 8/16, right? Which is a half. So is that bigger than 1/16?
Yeah.
That's bigger than a 16, bigger than a 16, bigger than a 16, bigger than a 16, right? All those. So all of those together, right, would be like 1/16 plus 1/16, dot, 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 all the way till I get to this last one, 1/16. And all those together are a half. That's 8/16 put together. Yes? And I could continue this, right? Where would the next one stop?
32.
At 32. Right? I'd go out to 32. 1/32, and I'd have 16 of those. Make sense? And so what we're saying is that this sum up here is bigger than, right, is bigger than 1 plus a half 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 forever, right? Well, if you just keep on adding a half forever, what do you get? 1/2 plus a half plus a half. That's becoming huge, isn't it? Because those aren't getting smaller. Like 1/2, 1/2, 1/2, same number. It's just going to overfill. So this sum right here is infinite, and this one has to be bigger. So the only way you're bigger than infinity is if you're infinite yourself. I hope that's convincing enough for you. Yay or nay?
Are you saying that infinity goes on the left?
Saying infinity is greater than infinity. This is infinite, and that sum's bigger than that, so it has to be infinite. Because infinity is an idea, right? It's not a number. So it's not like me writing 4 is greater than 4. It's not that. You know, writing infinity is greater than infinity just means that this side is bigger than that side. They're both getting big, but this one's always staying bigger than that one. Okay? So, yeah. All right, so what would happen if we change this to C? If this was C now, well, you know what? Let's make it super easy. How about this? If this was C, how about we pull the C out of the, there, I'll make it real simple. C comes out, right? So this is C times all of that, right? And then I could just put a C out in front of that. And so this is C times infinity. Still maintains the inequality, so I think that suffices. Okay? All harmonic series diverge. So that ends what's going to be on the test.
Can you give like an example of something that you just described, like a problem?
Yeah, that's I was going to. Let me see what I want to do here. The harmonic ones aren't very interesting. That's the thing. I mean, there's...
Maybe you could put something that, you know, similar to what you would look for in an exam. So you can kind of bring something up.
Okay, here we go. No, that's not going to work. They don't have many harmonics in here. Increasing?
Yeah, like they're always addition? Or can they always?
They're always addition. Yep, the harmonic is always plus, plus, plus. There's no alternating in there. However, if it does, we'll be able to deal with that next section. Okay? I mean, I don't know. I don't know what to give you other than something like this. I don't know, like there. What does that do? It diverges.
No.
Yeah, it's just a recognition of what it is. That's all it is. Right? It's not like geometric where you have to massage it and make it n-1 and figure out what A is, and you don't have to do any of that. You just have to look at it and be like, oh yeah, it's harmonic.
So that's all we have to write?
Yep, harmonic.
Divergence.
Yep. But it better be harmonic.
And when we take the absolute value of a to the n, it goes to 0, then a to the n converges to 0. It looks.
Wait a minute.
It looks similar to like, when we, how's that different? Like, why does harmonic? I can see the math, but like when we do the absolute value, is this something different?
Well, if we take the absolute value of this, right? So you're going back to what we call the Nth Term Test, right? Which is the first test on that list that I gave you, right? It says that if the limit as n goes to infinity of a sub n is not equal to 0, then what? Then the series diverges. That's the Nth Term Test. Right? That's the first test on your thing. So if we look at this right here, and we take the limit of that as n goes to infinity, we get 0. Right? This test tells us nothing then. Right? This is a test for divergence. What we need is for that limit to go to something other than 0 for us to use the test. I don't know if that's what you're asking me.
No, that helps.
Okay. So look at this one right here. Let me give you a slight difference here. I saw another hand go up, so hold on. How about that one? Is that harmonic?
No, it's with the n.
That is not harmonic. Okay? It's not harmonic. In fact, this series, well,
Why couldn't it be harmonic?
well, what does it mean to be harmonic?
It has to be a non-zero real number.
Constant on top.
It's a constant on top and a linear expression in the bottom, right? And here you have a linear expression on top and linear expression on bottom. However, it still diverges. This one diverges. Why? Why does this one diverge? It's not geometric, right?
Infinity over.
Because if you do this test right here, if you look at this and you take the limit as n goes to infinity of this, what do you get? Infinity over infinity, L'Hopital. 1 over 2, 1/2. Is 1/2 not 0? Is 1/2 not 0? 1/2 is not 0. Divergence, done. This diverges. Okay? Yes?
If it was 7 over 2n minus 1, is that harmonic?
That would be harmonic. The question is, what if it was 7 over this? It is harmonic, but I'm intentionally right now leaving off anything here because we have to convince ourselves that it will still be harmonic, but it is. It turns out, later on, I'm just going to say this. Any constant over any linear expression in n. Any linear expression in n, constant over any linear expression in n will be divergent. But I'm just not ready to say that yet. Right now, it's just constant over n. Yes? Well, y'all came with the questions today. This is good.
Linear means not to an exponent, right? It can't be like n squared and.
That's right. Linear meaning not n squared, square root of n. Linear meaning n to the first power.
Once that fraction gets to the point where it equals, like, say, 14 or 21 or 28, would it reduce it in the series, or do you keep it 7 over 21, 14 or 21 or 28? Because then it would no
What?
longer be
What?
the same constant.
What? I'm not
Like
fine.
if the denominator became an even, like a factor of 7, like 14, 21, 28, and it reduces to, say, 1/2, 1/3, 1/4, whatever, doesn't that technically change the 7 from it being a constant of 7 to something else, meaning it wouldn't be harmonic?
No.
No.
Because you're not looking, the formula C over n is the formula for a sub n, for the nth term of the sequence. Okay? You're talking about a specific term in the sequence.
Okay.
Yes, there are times within that sequence where it doesn't look like 7 over something, but that's only because fractions reduce, right?
Mm-hmm.
Okay.
Anyway.
Yeah. Yes.
On the homework you had, I saw somewhere it was like.
That's a scary shirt.
A what?
That's a scary shirt you've got on. I'm just messing with you. I like it. Go.
It's where we had like partial fraction. Was that harmonic? Where it wasn't a linear, but we did.
Well, we haven't done that yet.
Oh, okay.
Yeah, that's why on the homework I said to stop at a certain point. You're talking about telescopic collapsing, which is what I'm about to do now. Okay, is that it? I like answering questions, but you know, let's not. We're gonna do the whole semester's worth of questions today. Go ahead. I said what, 12? Yeah, just to go through number 12
So 5 through 12.
for 8-2. Yeah, I said that right at the end of class. Okay. I thought I saw another.
Was he referencing two linear factors?
I believe he was talking about when you have two linear factors in the denominator. Chris, that's what you were saying when you have two linear factors and we use partial fractions?
Yeah.
Yes. Yeah, that's what he's talking about. Okay, so before we move on to the next type of series, so this is your second common series. Harmonic is like super easy. You look at it, harmonic, divergence, move on.
That's gonna be the whole test?
Yeah, I can give you 30 harmonic series and ask you to find convergence or divergence, yeah. And then when you're done, I'll have your electrical engineering degrees and computer science. I just have them right here. You just sign them and
Civil for me if you don't want.
so yeah, whatever you want. We just show up. Just show up. Okay. So, here they are. Okay. Where are they? Come on. Where are those properties? All right, well, I'll just take them out of the book. Okay, a couple of properties we need before we move on. Suppose, that means suppose. All right, I'm trying to shorten this little property thing, but so notice on my notation I've gotten a little sloppy here. It's not me, it's the book does this also. Instead of writing sum n equals 1 to infinity, if we just write the sum, we just understand that we mean from n equals 1 to infinity. All right? So this property says, look, suppose that you have a convergent series and you have another convergent series. Then the following are true. First of all, if you multiply this convergent series by a constant, it still converges. So does means these also converge. So if you take two convergent series and add them or subtract them, you still have a convergent series. All right? That behaves the way you think it would behave. What's important to understand, though, is that this doesn't work for divergence. So let's say that this was divergent and this was divergent. Then if we add or subtract two divergent series, we don't necessarily get a divergent series. All right? That's important. It's very important. This only works with convergence. So now let's take a look at a new series. It's in the book. It's all on page 441. So this is your first example of a telescopic or collapsing series. Okay, here we go. Now these series are very different than geometric and very different from harmonic. in the sense that with geometric, it's kind of like you see this pattern, you make it look like a times r to the n minus 1. With harmonic, you're just looking for a constant over linear, basically, and you're like, oh, it diverges. Telescopic, each one is kind of its own little animal, but they all have something that happens within them that makes them get this name. And you'll see it as I work through a problem. So here we go. We're going to do this one. Sum n equals 1 to infinity of, let's go with 1 over n squared plus 3n. So let's start thinking more like a student who's been looking at chapter 8 for a while. First thing I'm going to do when I look at that is I'm going to run the nth term test real quick. So what does the nth term test mean I'm going to do?
Infinity. Take the limit.
Take the limit. So I'm going to try nth term first. If I do the nth term, that means I'm going to take the limit as n goes to infinity of 1 over n squared plus 3n. And what is that limit? What does that limit equal? 0. So what does the nth term test tell me?
Converges at 0.
Nope. Tells me nothing. The nth term test is basically does not apply to this, right? Since this is 0, the test, this is that pregnancy test that doesn't work, right? That's basically what happened, okay? So what do I do next? Well, I think about geometric, right? All right, geometric. Is this geometric? Well, geometric, all of them had, the exponent was the n, right? Like the n was up in the exponent. And so this right here is not like 3 to the n or 4 to the n or something like that. The n is down in the base. Yes? So this can't be geometric. Okay, so then I start thinking harmonic. Is this harmonic? Well, is it a constant over a linear expression in n? It's not. So it's not harmonic. All right, so those are all off the table. So what do I have left? Well, the only other thing we've done is telescopic. Well, we're doing it right now. But do you see, this is kind of like the way you want to start processing these series. Start running through kind of a flow chart of concepts. Yes? Okay, so now, is it telescopic? Well, I need to show you how telescopic works. What we're going to do is we're going to rewrite the series. And we're going to just do some algebra. We're just going to factor, right? Just factor that out, that n. And then let's go back and let's recall some stuff we did when we were doing integrals. We had that thing of partial fraction decomposition, right? And it gave us a way of taking 1 over n times n plus 3 and rewriting that as a over n plus b over n plus 3, right? I mean, we do have ways of splitting this up, right? And if I split it, then this one right here, imagine that this were written that way, right? 2 different pieces. Then maybe I could use that property that I just put up on the board that as long as they converge, you can put them together or split them apart, right? Okay, well, let's see. We're going to have to go through and do this work, right? So this work, you bet 1 is a times n plus 3, and then plus b times n, right? I'm trusting you could do this. I'm going to do the shortcut. Let n be 0, and then a would be equal to, 1 would be equal to 3a. So I'm going to get here a is a third. Again, I'm trusting you could do this part. And then I'm going to let n be negative 3. If I do that, we should get b is negative 1/3. Not showing much work here. All right, so if I rewrite this, right? If I rewrite this, I get sum n equals 1 to infinity. And now that expression becomes 1/3 over n. Then I'll write it this way, minus 1/3 over n plus 3. Are there any questions on where I got any of this? Y'all went quiet again. Okay. So we're all happy. Okay. Partial fractions, get your constants, rewrite it. Now, there is a property that allows me to split these up, right? Right? So long as they converge, I can split them and put them back together. So long as they converge. So if we look at this right here by itself, does that converge or diverge? 1/3 over n. What type of series would that be? That's harmonic, and harmonic series diverge, right? That's divergent. And that by itself, we haven't got too much into it, but again, doesn't this look very much harmonic? Right? But right there, just right off the bat, that right there, it diverges. So you are not allowed to split this up into two. You cannot do it. Right? So what do we do? Well, how about this? Can we do this? Does that seem like a fair move right there? They each had a 1/3, right? So I can just pop that 1/3 out of the whole thing? Yes?
Quick question. If
Yeah.
I take the limit of 1/3 over n,
Mm-hmm.
wouldn't that give me 1 over infinity, which is 0?
Yes.
So that means it converges, but we don't know.
No. That means that the sequence converges. That doesn't mean the series converges. So what you're saying, Chris, is what the most common problem I see with these. Students want to just take the limit of this and then say that's 0 and be like, then the series converges to 0.
Yeah.
No. If this converges to 0, you know nothing.
Yeah.
Okay?
No, I just meant like, because you said it diverges, but just from the test, you know, doesn't it mean that it fails? So
No. The test gave us 0, right?
So we don't know anything.
So we don't know anything. It could still converge or diverge. There's a different, it's a bad pregnancy test. It doesn't mean you're not pregnant or pregnant. It just means you don't know yet,
So
you know?
Mean it converges, though.
It does not mean it converges.
That's what I thought.
Okay, good. So the nth term test is a test for divergence only. It would be like a pregnancy test that only tells you if you're pregnant. Okay?
So we're going to the doctor.
Everyone's going to the doctor. Okay? So is that a good analogy? A test that would only tell you if you're pregnant?
That's the same thing.
Why?
Because it's divergent.
Yeah, okay. All right. So anyway, yeah.
See my con?
All right. So either way you look at it, right? So if that thing goes to 0, you know nothing at all. But what I was saying is if you look at that as a series, that's harmonic and diverges, right? So we can't even use the thing where we split it apart into two sums. That would be nice. If these were both convergent, then it would be nice to just split them both apart and then just do them individually. But it's not, so we're stuck. So I pulled a 1/3 out. Is that all right? Everyone kind of agree with that? They both had a 1/3? Okay, so now comes the thing that makes this telescopic. I'm going to start. You're going to need a lot of room for this. Make sure you have some horizontal space on your page. All right, so since we have no idea what's going on here, what we'll do is we're just going to start writing this series out. So I'm going to plug in 1, then plug in 2, then plug in 3. Okay, you ready? So this series is 1/3 bracket, and now just start letting n be 1, then 2, then 3. Okay, here it comes. When I plug in 1, what do I get? 1 over 1 minus 1 over 4. Okay. Now plus. Now we let n be 2. What do you get? 1/2 minus 1/5. Right? Plus what? 1/3 minus 1/6. How far do I need to go here? Oh, let's just keep going. You don't even know why I'm doing this yet, do you? 1/4 minus 1/7, right? Next. 1/5 minus 1/8. Next one, 1/6 minus 1/9. Okay, I would like you to just do that. Just continue that to infinity. I'm going to come back next week.
Are you trying to show like what you did with the harmonic one?
Not, well, kind of. There's something happening here. There's something happening. So I'm going to put plus dot dot, but it's not the harmonic. I was trying to show you that these sums were all bigger than like half plus a half plus a half. Here, there's something even more interesting happening. Does anyone see it? They cancel out. What do you mean they?
So like you have 1/5 there, negative, positive 1/5 there.
Yeah, like there's some things that are going to kill each other off. Like you see this negative 1/4? It appears over here as positive 1/4. I'm going to draw a little arrow connecting these. Do you all see that those two are essentially gone? Yeah? And you notice that with the 1/5 also, right? Negative 1/5 and positive 1/5. And the negative 1/6 actually got killed off with this one, right? Is there another one that would get canceled? It's negative 1/7, right? Would get killed off by what? The next one in this dot, 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 right? And the negative 1/8 should also get killed off, shouldn't it? Do you all see that? This negative 1/8 should get killed off by this something that's sitting in this dot, dot, dot. How about the negative 1/9? Yep. It should get killed off by something that's over there, right? So what are the things that did not get killed off? This one never got killed off. The half never got killed off. And the 1/3 never got killed off, right? Everything else seems like it goes away. So listen, I want you to listen to the words coming out of my mouth, all right? What movie is that from?
Rush Hour.
Yeah, do you understand the words coming out of my mouth? Okay. There's a pattern here. The pattern is this. Second terms within the parentheses, second guys kill off first guys, how many down? Second guys kill off first guys, how many down? How many pieces down?
6.
3 down. Second guys kill off first guys, 3 down. Second guys kill off first guys, 3 down. Yes? That's the pattern? Second guys kill off first guys, 3 down. So if you're a first guy, how would you get killed off? By a second guy this way, right? If you're a second guy, right, you kill off someone over there, right? So this is a first guy, right? To kill him off, he needs someone to his left, and there is nothing to the left, right? This is a second guy. He kills off the first guy, 3 down, right? Okay, so if you've got that pattern established, we're not done, all right? All we've done right now is we've established a pattern. Yes?
That pattern because of that plus 3.
Because of the what?
Is it because of the plus 3 in the denominator?
Yeah, it's because these are essentially the same expressions. At different values of n, they are the same expressions, right? So when n is 1 here, well, let's say when n is 5, right? That would be 1/5. But if n is 2, that's 1/5 here. So they match up at certain places within the series. All right, so this in no way has led us to the answer. Okay, we're close though, all right? So here's what we need to do. Recall that I wrote this on the board earlier. S is the limit as n goes to infinity of S sub n. I said I was going to use that later. I said if a series converges, then what I need to do is take the limit of the nth partial sum. So right now what I'm going to do is I'm going to stop. I'm going to realize I've established a pattern, and I'm going to write down what the nth partial sum is of this series. The nth partial sum is 1/3. And then isn't it this right here, this line? this, but actually stopping somewhere, right? Stopping at n. So I'm going to write it down. So this is where you need a lot of space. This is 1 minus a fourth plus a half minus a fifth plus a third minus a sixth plus, I'm going to go one more, 1/4 minus a seventh, maybe one more, 1/5 minus an eighth. Okay, that's the first few, right? That's enough for me to establish the pattern. Plus, dot, dot, dot. And now what I'm going to do is I have to stop, don't I? I have to stop this sum. So way out here at the end, I'm going to stop the sum. And where am I going to stop it at?
1 over n.
At n, right? I'm going to stop this at n. So what would happen if I plug n into that formula? I get that, right? So my last term is this. Is 1 over n minus 1 over n plus 3. Agree? All right. Okay. I would like to write out the few that are in front of it. So what is the one that's right in front of this one?
1 over n minus 1.
It's one less than this, right? So 1 over n minus 1 minus, and then I take 1 away from this, so 1 over n plus 2. So n plus 3 take away 1 is n plus 2. And then I want to write the one in front of that one. Why am I still writing more in front? The pattern, right? Didn't the pattern require the second one kills off the first one 3 down, right? So I need to be able to see at least 3 down from this. So I might run out of room here. What's the one in front of this one? 1 over n minus 2 and minus 1 over n plus 1. So everyone see I'm just subtracting 1 from each of these denominators as I move over? I don't think I have enough to establish the pattern. I've got to go one more back. I didn't give myself quite enough room. Just remember there's dot, dot, dot in here. What's the one right there? 1 over n minus 3 minus 1 over n. Okay, do you all agree that that's the nth partial sum? It's not pretty, but do you all agree that's what it is? Okay, let's cancel. This negative 1/4 cancels with that positive 1/4, right? They're gone. That 1 doesn't go anywhere. That half doesn't go anywhere. Does this negative 1/5 go? Yes. That negative 1/5 cancels with that positive 1/5. Gone. Okay. How about this 1/3? Oh, that 1/2 stayed, right? What about this 1/3? Stays. Negative 1/6 goes. Cancels with something in that dot, dot, right? How about the negative 1/7? Something in the dot, dot, right? How about the negative 1/8? Something in the dot, dot, right? Okay, now let's go to the other end. Does this one go? Second ones cancel with first ones 3 down which way? To the right. There is no right anymore, right? There is no right anymore. This guy stays. That guy stays, right? Okay, what about this guy? This is a first guy, right? First guys get killed off by second guys down that way. And you can see it right here, right? That one and that one go. Yes? What about this guy? That's a second guy. Second guys need first guys 3 down to the right. That way. Do we have 3 to the right that way? We don't. This guy stays. This guy? Yes, he goes. He gets canceled out with something where? In the dot, dot. This guy? Stays. You would need something 3 down, yes? He stays. Okay, this guy? In the dot, dot. This guy? In the dot, dot. What has happened? We have this, this, right? The only thing we're left with, S sub n, is 1/3. And then we had the 1 plus the half plus the 1/3 from the beginning, right? From the front, there was some stuff. And then at the end, there's some stuff, right? Plus 1 over n plus, oh, sorry, that's minus 1 over n plus 1, minus 1 over n plus 2, minus 1 over n plus 3. Y'all agree? Yes.
So if you wanted to get rid of the 1/3, the reason to the left, there's no reason to the left. So is that-
What 1/3? This one?
No, the other one.
The 1/3. Yeah, in order to kill this one off, we would have had to have had something over here, which we don't, right? Okay. So instead of having this huge sum, right, that goes out, what do we wind up, after all that canceling is done, we wound up with a little bit of stuff from the beginning and a little bit of stuff from the end, right? Everything in the middle did what? Collapsed out, fell out, like a bridge, okay? The center of the sum, the center of the series collapsed, and you're left with the two ends of the bridges, so to speak. So this is the collapsing series. Does that make sense? Telescopic, have you ever seen those old school telescopes where they look at them like that, and then when they're done, they come back together? Yes? Yes? So the two ends come together, telescope. Same idea. This end and that end, at the end of everything, they come together. That's where it gets its name from, all right? Now, we're not done, because that's just the nth partial sum. The original series, right? The original series, if it converges, is equivalent to the limit as n goes to infinity of that nth partial sum. So now what I need to do is take the limit of this. Let n go to infinity. Okay? So if I do that, if I take the limit as n goes to infinity of that nth partial sum, what does that go to? 0, 0, 0. And so all you're left with is the 1 plus a half plus a third. Yeah, I think I'm doing that right. 11/6. Oh, I forgot the 1/3. Yeah, there's a 1/3 out there. Thank you, thank you. Where did I put this 1/3? Put it right in front. Thank you. 1/3, 1/3, and so 1/3. This is 11/9, or 11/18. Sorry. Okay. So consider my next comment fair warning to you. All right, this is fair warning. If on the test you do the partial fractions and do all that, and then you write this line out right here, and you go, oh, dot, 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 and I see all I'm going to be left with is the front of this, right? Which really wound up being what our answer was, right? And you never show the nth partial sum, and you never actually show the collapsing happening inside, and then take the limit of this, you're going to, basically on a problem, if this were like 10 points, you're going to lose at least 6 points, 6 to 7 points on that. And here's the reason why. Not every one of these will have the tail end go to 0. In this particular example, this tail end, both these pieces went to 0, right? But there are some examples where the tail end doesn't go to 0. So even though this collapsing looks like, oh, it's just canceling, everything out there cancels, what winds up happening is there's some stuff out there at the very end that does contribute to the sum. So if you stop at this point right here, you could be wrong. So you've got to go through this formal process of coming up with a formula and then taking the limit at the end. Okay? All right.
Is this 8.4 technically?
Nope, we're still on 8.2. That sigh.